Hello, guys. How are you? Today we will be our second lecture of Design of Steel Structure course. Today, the topic of Module 2 is Structure Analysis and Limit State Design of Steel Structure. And today we will have 5 topics. The first one is Material and Design Requirements. Second topic is Structure Analysis and Design of Steel Structures. The third topic is Limit State Design. The fourth topic is loading and load combination on structures. The first topic is load estimation on structure members. Today I will focus only on the equations part and numerical problems, but I will go through the topics briefly. Our first topic today is the material and design requirements of steel structures. Here we are talking about some properties of steel and different cross-section. And here is the different between cold formed steel and hot rolled steel. And as you can see, here is example of hot rolled steel and some example of cold formed steel. This is a channel section. And you can see that the hot rolled steel are thick compared to the cold formed steel, which is thin structures or thin members. In this video, there is a comparison between the process of manufacturing of hot rolling and cold forming. And I think you have already seen a similar video in the first week module. In point 3, this is a comparison between cold formed and hot rolled steel. In hot rolled steel, we have some common section in the Australian market, which are universal beam, UB, universal column, UC. Universal beam is close to I section. Universal column is close to H section. The difference is the width of the flange. And we have also channels or C sections. So we can have C sections. Equal and unequal angle, equal angle or unequal angle. All these are common sections in hot rolled steel. We have also cold formed steel section, like circular, square, rectangular hollow section, circular hollow section, square hollow section, and rectangular hollow sections. And also we have compound section. In addition to this, we have also channels and Z sections. So we have C sections and Z sections under cold formed steel. We have also compound sections. Compound section are combination of two hot rolled steel or hot rolled steel like UB section, and we weld some plates on top or on bottom, so it is strengthened with some plates. So this is also some cross section available. You can make it yourself if you want a stronger section. We have also built up section, which can be produced by welding plates together, forming I or H or box members. Example of this are plate girders, which we have introduced last week, built up columns, box girders, or columns. We have also some built up cold formed sections like purlins, side and sheeting rails. And in this figure, there's some examples for the plates and standard sections available. So we have hot rolled plates and I section. This is plate, this is UB, this is UC, this is welded beam, this is welded column, this is tapered flange beam. And we have also hot rolled channels and angled and bar. So we have parallel flange channel, equal angle, unequal angle, flat bar or flat, square plate, round plate, or round bar. So all of these are examples of hot rolled. We have also some examples of cold formed steel, like circular hollow section, rectangular hollow section, and square hollow section. This is another common section for beams. We have hot rolled in A, hot rolled universal section. Second one is welded. So you can see here there is a small weld between the plate, the web and the flange. So you have several examples of common section in the market for beams. In this point, we are talking about physical properties of steel. So we have the stress strain diagram for mild steel and low alloy steel. You can measure the properties of steel using tensile coupon. Like this is you can call it coupon or dog bone. Okay, so this is our coupon. So the coupon test or tensile coupon test is you have a dog bone like this one. This is the sample, and the size of sample depend on the type of steel under tension. So this sample will break at the or nicking at this area with a small thickness or small width. So you can measure or plot a relation between stress and strain for steel. And as you can see, this is how the steel behave under tension test. You can see this is yielding point, and also this is nicking, and then strain hardening, and then this part is failure. Okay, this is explanation of terms in the stress-strain relationship. You have elastic limit, elastic range, plastic range, reduction in area or nicking, strain hardening range, ultimate elongation, ultimate tensile strength. So the two main properties we need for steel is F yield strength, and F ultimate tensile strength, or the stress when the steel break. Young's modulus E. E is a constant for steel. E is equal to 200 gigapascal. So any type of steel, the Young's modulus is 200 gigapascal. In this video, this is an example of testing steel or standard tensile testing of steel. So please watch this video. In this point, we are talking about the steel properties under ambient temperature and also under elevated temperature. So yielding stress is the main properties we are looking at. So in this table, you can see here, this is the properties of steel under room temperature. So you can see E is 200 gigapascal or 200,000 MPa. The shear modulus G is 80,000 MPa. the coefficient of thermal expansion, alpha T, is 11.7 times 10 to the power -6. The Poisson ratio for steel is 0.25, so this is also constant. So this is constant, this is constant, this is constant, all of them are constant. The density of steel raw is 7,850 kilogram per cubic meter. In this table, we'll see the properties of steel under variant elevated temperature, and you can see how when you increase the temperature, what happened to the properties? Decrease. So as you can see, at 500 Celsius, this is the reduction factors for the Young's modulus E and the yield strength F yield. In this point, some specification and strengths of typical steel. So some important consideration regarding the type and the grades of steel you need to keep in mind: the weldability, ductility, low cost to strength ratio, availability of sections and plates. So when you choose a structural steel, you need to keep in mind this 4 properties or 4 characteristics of steel. Because we have different steel types and grades. So steel types and grades based on AS 4100, and in general, thinner plates generally have higher yield strength. And these are the available steels in Australia. So you can see there is some steels like complying with the Australian standard for hollow section. Some of them are complying with the Australian standard for hot rolled and plates. So you can see here we have some grades like C450, C350, C250. This for hollow sections. And for hot rolled, we have 450. This is the yield strength. 400, 350. As you can see here, for 400, you can see the yield strength is 480. Here 350 is 450 yield strength. Sorry, this is the tensile. So the grades of steel, hollow sections, C450, C350, C250, and this means yield strength of steels. So these 3 types. Also for the hot rolled steel, should be complying with the Australian standard for hot rolled steel, and the grades are 450, 400, 350, and you can see this is 450, this is a 400, and this is the 360 or 350. So the grade of steel mainly depend on the yielding strength of steel, and you can choose which type. As a designer, you can choose which type of steel you are using or available in your area. There are some other structural steel properties which we need to know, like the residual stresses, which is stresses that remain in unloaded member after being formed into a finished product due to cooling effect after hot rolling or welding. So the residual stresses are important properties we need to know in steel because it affects the behavior of members. And as you can see here, this is some example of residual stresses in hot section. So the residual stresses are due to the hot rolling process of steel. The second property we need to know is the fatigue. The fatigue is when structures subjected to many cycles of load, more than 11 or 100,000. So this causes the material to weaken, and then failure occurs by continued growth of cracking at stresses below static yield strength. So in some cases, the steel will, due to fatigue, will fail before reaching the yield strength because of fatigue. So fatigue is unlikely in normal civil engineering structure, but in some structures under like repeated loads or dynamic loads, the fatigue is important thing to care about. Also, the brittle fractures. Steel becomes brittle when the temperature drops below 100 Celsius. The fracture can occur at low stresses below 0 Celsius. So when the temperature is negative, so the steel will be susceptible to brittle fracture. So under low temperature, the steel is more brittle than ductile. The next property is the fire protection. Steel performs badly in fires and high temperature. Strength decreases with the increase in temperature. At temperature of 550 Celsius, yield strength falls to approximately 0.7 of its value at normal temperature. Fire protection can be provided by encasing member in concrete. So this is one of the solution. Encase the steel in concrete or cementitious fiber materials. Like if this is the steel section. So if it is a column or a beam, so we put it in a concrete section. So the concrete is more or better in fire protection. So it will be better in if the steel member under fire. The other option is bending to the exposed steel work. So intermittent bend, this type of bending that helps the steel to resist fire better. The second or the next property is the corrosion protection. As you know, steel is susceptible to corrosion due to environmental conditions like water or vapor or air. So provide surface protection like metallic coating and bending, careful detailing of steel structure to avoid alternate channels forming cavities to collecting water. Like don't put structure like this, like C channel like this, if this is the roof or something. So if the water come here, so the water will stay here and cause corrosion. So better or careful detailing will help also to avoid corrosion. The next properties is transition from temperature. So the ductility of steel is normally tested at room temperature. Ductility diminish at lower temperature, brittle behavior. As we mentioned in the fracture, so when the temperature low, this causes the steel to be brittle. So you need to know at which temperature the steel is designed or used. The next topic is the structure analysis and design. So this topic is talking about the structure analysis and design of especially steel structures. So the first point is conceptual design process. In conceptual design, there is some steps you need to do. Like architects are usually responsible for problem formulation, and you have to keep some consideration into account, like identify the purpose of structure, amount of space enclosed, assessment of site, selection of materials, loading, local government regulations, corrosive environment. All these are points you need or things you need to keep in mind when doing the conceptual design process. The second process is the engineering design process. Designer core task to conceive the structure in accordance with the design brief, relevant standard, and other requirements, and ensure the structure will perform adequately during its design life. In this phase, or in this process, we have some phases like investigation phase, conceptual design phase, preliminary design phase, and final design phase, and documentation phase, tendering phase, and construction phase. So the construction process or the engineering design process has different phases, including the investigation phase, conception design, preliminary design, final design, documentation, tendering, and construction. So please go through this phases and let me know if you have any question. Topic on point number 3 is the structure design principle. In the structure design principle, we have to know the objective of structure design. So define the structure capable of remaining fit for the intended use throughout its design life without the need of costly maintenance. Appropriate methods appropriate methods of analysis to predict the strength and surface load of structure. Also, you need to know the codes and standards because it played important role in your design. So you need to stipulate minimum structure performance level under structure and serviceability that legally must be met. Reinforced concrete and pre-stressed concrete following or complying with AS 3600. The steel structures need to comply with AS 4100. Most decisions in design are interrelated, so the design process is iterative. You cannot design from the first try, so you need to make different like trials to make sure that the design is good or economic and the structure is complying with the standard. The next point is the structure design requirement. So the design requirement, the first point is serviceability, and then strength, durability, robustness, others, including fatigue, fire, resistance, vibration control, or any special requirement. And also there is non-structural requirement like the appearance and aesthetic. So all this need to be fulfilled under the design structure design. So in serviceability, you need to make sure that the structure will perform well under day-to-day surface loads without any excessive deflection or cracking. They also need to satisfy that adequate strength to resist the overloading and environment extremes, and also durability. So the structure don't deteriorate rapidly and can function without any undue maintenance and repair over its design life. Robustness is the ability to resist unexpected and accidental loads action, such as blasts and collisions. And that's it for the design requirement. The next point is structure modeling. Structure modeling, we have real life structures, extreme complicated and impossible to model. Idealized and simplified models are created for the analytical study of structure behavior. So you can't actually model the real structure, but you can like simplify the model to so that you can do it. Otherwise, no one can exactly model everything in the real structure. So we have analytic model. Analytic model is idealized and simplified representation of the complex structure, retaining its essential aspects and starting point of the development of any theoretical analysis. So analytical model is used for theoretical analysis and like modeling the loads and the material properties and supports and so on. The physical model is a small scale prototype using same material tested in the lab. So this is an experimental model. So we have an analytical model and experimental model, useful to study complex phenomena and complex structures. The next point is structure analysis. Structure analysis, the objective of structure analysis to determine the internal forces and moments so you can design. So you have statically determinate structure and we have statically indeterminate structure, more advanced method. Before desktop computers and structure analysis software are available, methods such as moment distribution were necessary, but it takes a lot of time and need mathematical effort. Now we have software packages like MicroStrand, SpaceGas, Multiframe, Strand 7, and so on. So you can use them to do a structural analysis and calculate the loads on the structure. It's crucial that the designer understands concept and can distinguish a reasonable output from ridiculous output, which indicates mistakes in the data and assumption. Some required input, frame geometry and members, connection properties and boundary conditions, design actions and permanent load, wind load applied to the structure, like the dead load, like what is the material of the roof or the floor. So if it's concrete, so there is a dead load for the concrete and also for live load depending on the usage of the building. So all of this will come in later in this lecture. The analysis output is design action, moment, normal, and shear forces. Also, you can get some deformations like deflections, rotations, and so on. Methods of structure analysis range from simple to complex depending on the structure form. So we have elastic analysis, plastic analysis. In plastic analysis, plastic hinge are assumed. For example, yield line analysis of the two-way span, so on. And the methods of structure analysis depend on degree of accuracy required. So depending on the accuracy, you choose which method you will be using. Time required to assemble data for rigorous analysis. Simple methods are usually employed in the preliminary design. So the simple methods are used in the case of preliminary design or the preliminary design phase. Here, the elastic analysis, we will be using elastic analysis because structural analysis, plastic analysis is complicated. So we are in normal design process, we using elastic analysis, which is clause 4.4 in AS 4100. So in elastic analysis, there is linear elastic analysis, which has been traditionally used as the basis of structural design due to considerably simpler analysis. And in this method, individual members are assumed to remain elastic, under the action of design loads for all limit states. So the main thing here is that the members remain elastic after any type of loading. The Australian standard required second order effect. This is important point here. So the Australian standard requires second order effect to be considered in designing of steel structure. So the design load acting on a structure in their displaced deformed shape configuration shall be considered through either first order analysis with moment amplification factor or second order elastic analysis in Appendix E. So we have two methods of second order effects introduced by the Australian standard. The first one is first order analysis with moment amplification factor, clause 4.4.2, or second order analysis in Appendix E. We are focusing on the first one, first order analysis with moment amplification factor. And this means that if you have load like this, or member under this load, so under this load, the member will deform like this. So when this member deform, the force here shifted a little bit with the value of the deformation. So you need to take the applied moment here, which equal to F by delta, which is due to the deformation. So this is what is meant by second order effects. So second order effects due to the deformation after applying loads. So you cannot consider that the member still same after applying load because it will deform, and this deformation will cause or add additional loads or moment to the structure. So in the first method, first order elastic analysis with moment amplification, provided moment amplification factor delta B and delta S, which will be less than 1.4, useful where manual analysis is carried out. So the first one is important because it is for manual calculation. The second method, second order elastic analysis, are attributed to geometry changes during analysis. Deformation of structure and design action affected are coupled. Second order effects can sometimes be small enough to be neglected, except in special structures such as unbraced multi-story frames. Computer programs such as Base Gas or Strand 7 can carry out first order and second order analysis. So if you want to do a second order analysis, you can do also it by software. Point number 8 is the forms of construction assumed for structure analysis. Distribution of design action through the members and connection of structure takes one of the combination of the following. We have rigid connection assumed to have sufficient rigidity to hold the original angle between the member unchanged. So if this angle between beam and column, so after deformation, it will stay like this. This means rigid. So this is for rigid connection. Semi-rigid connection is connection may not have sufficient rigidity to hold the original angles between members unchanged, but shall be assumed to have the capacity to furnish a dependable and known degree of friction resistance. These connections are more difficult to analyze, usually avoid in practice. The third one is simple or bin. Connection at the ends of members shall be assumed not to develop moments in simple construction. So in this type of connection, so it doesn't have to be to remain doesn't have to remain unchanged after the loading. So as you can see, the angle was like right angle, and after that it became it doesn't stay a right angle. So this is pin connection or simple connection. Design of connection shall be consistent with the form of construction. So this is example of rigid connection. You can see the connection is very strong to transfer shear and moment. But here, as you can see, it is simple connection because it is only transfer shear, but cannot transfer moment. Assumption for analysis, division into substructure. So because the structure sometimes are too big or large structures, so need to subdivide it. So analysis is regularly shaped many members can be simplified by treating substructure. Structure shall be analyzed in its entirely except as follows. Regular building structure may be analyzed as a series of parallel 2D substructure. Analysis being carried out in each of two directions at right angles, except when there is a significant load redistribution between substructure. So as you can see, this is a three-dimension complex structure, and it can be converted to simple structure, subdivided. Like this is a 2D frame in YZ plan, and this is 2D frame in XY plan. For vertical building and multi-story building, structure provided with bracing or shear wall to resist all lateral force, braced structure. Each level together with columns immediately above and below may be considered a substructure. Columns assumed fixed at ends, removed from level under consideration. So as you can see here, if this is the structure of multi-story building, but the main thing, it should be braced. So you can subdivide this to, can take the floor or the beam with the upper and lower column. So this is your substructure. These methods are just for simplification, because you have a complex structure and you need to subdivide to like simple structure. When floor beams in the multi-story building are considered substructures, bending moment at supports may be determined from the assumption that the floor is fixed at support. One is span away if the floor beam continues beyond the point. Also, this is considered fixed, so this is how to simplify the structure in multi-story braced building. Notes for subdivision. Subdivision should follow plans of weak interaction between substructure. Single-story warehouse building can be subdivided into portal frames and so on. Where the floor system is relatively rigid in its plane, frames are forced to deflect laterally by the same amounts, but otherwise carry the vertical load independently. Some frames are designed to interact in 3D and should be analyzed as one entity. So if the structure is designed as 3D, you cannot subdivide it. Rigidly joined substructure with no bracing element rely entirely on frame rigidity to remain stable. Connection must be designed to be able to transmit all actions with minimum distortion of joints. Such frames are usually initially analyzed by elastic or plastic first order analysis, followed by an assessment of second order effects to verify their stability against frame buckling. In this point, we are talking where or when to use second order or first order analysis. So the first order analysis is simple elastic analysis. The computational process ends with the determination of axial, shear force, and bending moments. Displacement of nodes are determined in the final step of analysis, but no feedback is included on the effect of changed frame geometry in successive steps of analysis. The Australian standard design 400 for 100 design action due to displacement of the frame and formation of the members action must be determined by a second order analysis. So the Australian standard required second order analysis in some cases. Or method that approximately second order analysis. Approximate second order analysis. In braced frame, sway deformations are often too small to be considered, but in unbraced frame, rely on the rigidity of connection, sway deformation cannot be neglected. So the second order analysis is important, more important in the sway frames because they are susceptible to deformation and the sway deformation can't be neglected. Sway is caused by lateral or asymmetrical forces. Asymmetrical means anti-symmetrical. Vertical forces, most often by inadequate stability under significant axial forces in columns. So if this is our frame, so this is called sway. Might be due to lateral forces or inadequate vertical forces. Second order analysis is generally not required in flexure member with negligible axial force. So if the normal force is equal to 0, so no second order effect. Tension members, triangulated frames in which member forces are predominantly axial and no transverse forces are applied between nodes. The second order effects are consider a single story rigid frame. If we have a rigid story frame, like in figure 2.9, first order analysis give us the moment M1 and the deflection delta 1. When both columns are deformed, no longer straight, forces B1 and B2 tend to displace nodes further right. So due to this, we have delta 2 and M2. So displacement and moments increase to delta 2 and M2 due to second order effect, or it's called B delta effect. So the B delta effect means second order effect. Interaction of axial load or axial compression and member curvature from flexure and sway deflection. So the second order effects due to B delta effect and the interaction between the B1 and B2 with the deflection delta 1 and delta 2. Okay. The next point is how to calculate the second order effect. This important point. So how to calculate second order effect. The first method is using computer software. So when you use computer software like Strand 7 or Space Gas, when performing a rational second order analysis, design action effect M star, V star, N star are obtained directly. All displacements are tracked during the process of evaluating design actions effects until all displacements converge. If convergence is not achieved, structure is unstable. No further amplification of bending moment needs to be applied. So this is how the method works. The second or the important method we will be using is the manual procedure via moment amplification factor as recommended by Australian standard. So the steps of this method are Step 1, elastic first order analysis. Step 2, calculate the moment amplification factors. So step 1, elastic first order analysis. Step 2 is the calculation of moment amplification factors for braised delta B, for sway delta S. Step 3, check moments amplification factors and need to be less than 1.4. Step 4, evaluation of design moments in member subject to axial compressions forces. M star equal to M by delta. Need to note that calculation of amplification factors is limited to members in rectangular frames. So this method is only applied or applicable for rectangular frames. Second notes we need to know is if delta more than 1.4, you need to redesign the frame or check with advanced analysis. So the amplification factor is not applicable here. Calculations of delta B. So the first thing we need to know is delta B, which is for braced frames. Columns in braced frame, columns and beam are braced. No sway under loads, no relative transverse displacement between end members. The first step or the first point is to determine the elastic flexure buckling load in OMB for each braced compressor member. So for each member, what you will do is using this calculation for each column, where E, Young modulus, I, inertia, Ke is the buckling factor, L is the length. The second step is calculate the factor of unequal end moments, Cm, where Cm equal to 0.6 minus 0.4 beta m and should be under 1. We will know these parameters soon. Point number 3 is to calculate the moment amplification factor for the braced member delta B, where delta B equal to Cm over 1 minus n star over NOMB and should be larger than 1. So delta B should be more than or equal 1 because it is amplification factor, so it cannot be less than 1. The next step is to check that delta B is less than 1.4, because if it is more than 1.4, you need to redesign the frame or make further advanced analysis. LC frame is very sensitive if delta B more than 1.4, so you need to do second order analysis or enhance the frame stiffness. So for LC frame means delta B larger than 1.4, you need to enhance the frame stiffness, which means redesign or second order analysis. The last step is to multiply to find the amplified moment. Multiply the bending moment from the first order analysis by delta B to obtain the design moment. So the design moment, delta star, will be the moment from first order analysis times delta B, which we have calculated and should be more than 1 and less than 1.4, where delta mm is the maximum moment in the considered member. So this all for theta B for braced frame. The next is delta S for sway frame or unbraced frame. So for unbraced frame, we have calculation of delta S for unbraced frame. But we have two methods. The first method is method 1. So we have two methods. This method 1 and we have here method 2. So in method 1, for delta S, columns generally for a sway frame, columns are sway, beams are braced, unless axial compression is significant. So for delta S is only for columns. Moment amplification factor for sway, delta S, and delta S, and this method is only, again, as a reminder, regular and rectangular frames. So this equation, delta S equal to 1 over 1 minus C3, where C3 is delta S times summation N star over HS summation V star, where delta S transitional displacement of top relative to bottom story height HS from first order analysis. So if this our column, the height of the story is HS, so this is HS, this is HS height, and delta S is the transitional displacement of top relative to bottom story height. So this is delta S. If this 0, for example, and this delta, so this is delta S. Okay. Summation N star, summation of all design axial force in the story under consideration. Summation V, summation of all column shears. So N star is axial forces and V is shears in the story under consideration. Note that this method is generally conservative and it terms story shear displacement moment amplification factor. So this method is called story shear moment amplification factor. Method number 2. Method number 2 for delta S. So alternatively, delta S can be calculated from elastic buckling load factor methods, especially when first order deflection are known. So if you know the first order deflection or deflection from first order, you can use this method number 2. If not, so method number 1 is better or easier. In this method, delta S is equal to 1 over 1 minus 1 over delta ms, or 1 over 1 minus 1 over lambda c. So delta S equal to 1 over 1 minus 1 over lambda ms equal to 1 over 1 minus 1 over lambda c, where lambda ms is the elastic buckling load factor for the story under consideration, and lambda ms equal to summation NOMS over L over over summation N star over L. So summation each member or NOMS for each member over its length over N star over its length. So this is equal to lambda ms. As you know, NOMS is the elastic buckling load factor for a sway member, which equal to pi over pi square EI over K L all squared, where L is the member length or story height, N star is the member design axial force. Tension is considered as negative. And sum includes all columns in a story. So N star here in this equation, you should, if the column is under tension, if a column under tension force, let's say like this. So in N star calculation, this should be taken as negative. So it will be subtract, not added. Lambda C is the elastic buckling load factor determined from the rational buckling analysis of the entire frame. Lambda C is equal to the lowest of all lambda S values for a multi-story rectangular sway frame. So lambda C is the lowest lambda MS. Similarly, multiply the bending moment from first order analysis by delta M to obtain the design bending moment. So M star will be equal to MM times delta M, where delta M is equal to delta B if delta B more than delta S. Otherwise, delta M equal to delta S. So delta M equal to delta B if delta B more than delta S. Delta S equal to, or delta M, sorry. Delta M equal to delta S if delta B less than delta S. Okay, which means that delta M is the lowest of delta B and delta S. Is the largest, sorry. So delta M is the largest of delta B and delta S. Also need to note that if delta M, S or delta C more than 3.5, this means that delta S will be more than 1.4. So again, we need to perform second order analysis or enhance frame stiffness. So another indication of that this method cannot be applicable, delta MS or lambda MS or lambda C more than 3.5. This calculation should be carried out by member to member as or on a member to member basis. One of the parameters we need to know for this calculation is KE, or buckling length factor or buckling factor. We have two methods of calculating KE. The first one is the idealized KE, which is like for ideal conditions. In this, we have two types, braced and unbraced or sway. In braced, we have this column, and this column. The first one is fixed bottom and fixed at top, and KA is 0.7. And we have bin bottom, bin top, and we have K is 1. The middle one is one fix and one bin, so it is in the middle 0.85. So this is K. For the sway members, we have also 3. One of them is fixed at bottom and rotation fixed and translation free at the top. One is fixed at bottom, free at top. One is hinge at bottom and rotational only fixed at top. So this one we have fixed at bottom, rotation fixed only at top, which is 1.2. And we have same one but hinge or bin at bottom. This one we have 2.2. And the middle one we have fixed at bottom, free at top, which is 2.2. So this is the idealized values of KE. where LE equal or L buckling length equal to KE times L. So KE is the buckling length from this table. L is the column length from uh, the original structure or the real structure. Okay. And the second part or the second method of calculating KE is using the Stolen standard. This for rectangular frame and this table, these two curves is to calculate KE. So here is KE. To calculate KE, you need two things: stiffness at end one and stiffness at end two. Stiffness at end two, stiffness at end one. So each column, as you know, has end one and end two. So you need to know gamma 2 and gamma 1 and using this table so you can get KE. So we have first table is for braced, second table is for sway. So again, to know or to enter this table, so for example, if we have gamma 2 equal to 1, so if gamma 2 equal to 1, so we will get a line vertically like this. And let's assume that we have gamma 2 gamma 1, sorry, gamma 1 equal to, so gamma 2 equal to 1, gamma 2, gamma 2 equal to, sorry, here, gamma 2 equal to 1, and gamma 1 equal to 1.5. So at 1.5 here, we get straight. So they intersect here. So this is KE. So if we look at KE here, KE is equal to 0.8. So for example, if you know gamma and gamma, so you can get KE as 0.8. So how can we get gamma? Gamma is the stiffness ratio of compression member in rectangular frame with regular loading and negligible axial force. Gamma is equal to summation I over L for all columns divided by summation beta E I over L for beams. So this is gamma. So for each end, you need to do this calculation where summation I over L is the summation of stiffness in the plane of the bending of all compression members rigidly connected at the member and end under consideration, including the member itself. Okay, let's say we have this building. So this is our column. So we have this is like multi-story. So here, let's say this gamma 1, the top end or gamma top. How many members we have? We have, let's see, C1, C2, B1, and B2. So what you need to do is summation of the column C1 and C2. So summation I1, I2 over L1, L2. This is the columns. For the beams, you will have to summation B1 and B2. So on the bottom, summation BE, I, let's say IB1 over LB1 plus IB2 over LB2. And that's it. Okay, so summation BEIL for beam is summation of stiffness in the plane of bending for all beams rigidly connected at the end of the member at concentration. So this is an example of how to calculate summation I over L for column and beam. And here is the values of beta E. The values of beta E is for bin 1.5 for braised, and for sway is 0.5. For fixed, it is 2 for braised, 0.67 for sway. Usually connected to a column, 1 for braised, 1 for sway. Okay, so this is how to calculate beta E for the gamma calculation. So we use beta E for gamma calculation. Notes: contributions of any being connected to the shall be neglected. So you can neglect the being connected. Modifying factor beta E accounts for condition at the far end of beam. Columns with ends rigidly connected to footing fixed base is gamma equal to 0.6, because in some cases the column, this is the column here at the end, like gamma 2, is footing or the foundation. So gamma will equal to 0.6 or gamma equal to 10. So gamma equal to 0.6 in case of fixed base, gamma equal to 10 in case of bent base. So as you can see here, if the columns with ends not rigidly connected to footing, or we can say bin based, so gamma will be equal to 10. The next point we need to know is calculation of Cm, because Cm is required for calculations of, if we go back, Cm is needed here, or this is Cm needed for delta B. So the next step is how to calculate Cm. Cm, highest moment amplification factor, occurs when the bending moment is uniform along the member. So Cm equal to 1. Again, what is Cm? Cm is a factor of the moment under or on B, or on the member we are considering. So if we have column or member like this, we have M1 and M2. So we need to calculate Cm is a factor of moments, or in the moments of the member. So Cm equal to 1, because Cm or we just need to interpret this one. So Cm is the highest moment amplification factor, occurs when the bending moment is uniform along the member, which means theta m equal to 1. Cm for a braced member, we will know why this one happened here. Cm for a braced member equal to 0.6 minus 0.4 beta m less than or equal 1, where beta m is the ratio of a smaller bending moment at the member ends. So beta m is equal to m1 over m2. Okay, so if you have m1 and m2, so theta 1 is equal to, or beta m is equal to m1 over m2, where m1 is the smallest M2 is the large. Because in some cases, sometimes maybe M1 is equal to 0. Let's say, remember the moment here is 0. So beta M in this case will be 0 as well. So beta M is the smallest moment over the largest moment. After we get beta M, so you can get Tm. When we have some sign for beta M, it can be positive or negative. When beta M positive, when beta M is negative. When member is bent single curvature, beta M is negative. When member bent reversible or double curvature, beta M is positive. So what is the meaning of single curvature or reversible or double curvature? These are the two cases we have. In some cases, if the moment like this, let's say this M1 and this M2, so the bending or the beam will bend in this direction. Okay. So this is called single curvature. So single means negative. So in this case, beta M will be negative. Okay. The other case is if we have this is M2 and this is M1. So what is the shape of curvature we will have? This one will go like this, bend like this, and this one will bend like this. So this is positive because it is double curvature. So beta M is positive or negative. Positive in case of double curvature, negative in case of single curvature. This case means beta M equal to -1 for moment uniformly distributed. Like if you have a beam or column like this, here M and M, it is uniformly distributed. So beta, how much beta M? Beta M will be 1. But because it is single curvature, so it should be -1. Okay. The next one is beta M equal to +1 for moment varying along the member from positive to negative M. So if we have another, but here M and here equal M. So in this case, beta M will be M over M. It will be 1 or -1 or +1. +1 because this is a double curvature moment. Okay, so this is how to calculate beta M and Cm. And these are example of what we have been saying here. So this is the moment distribution. If you have some cases, this is double curvature. So as you can see, beta M always positive here. Here is a single curvature, so beta M is a negative. Okay, and using beta M, you can calculate Cm because, again, just a reminder here, Cm equal to 0.6 minus 0.4 beta M less than or equal to 1. Okay, so all these are examples, and now we can know how to calculate beta M. If you know beta M, so you know Cm. So the last point in this part is the limitation of moment amplification factor. What is the problems or drawbacks with moment amplification factor. Moment amplification factor method can be applied to most rectangular frames with the following conditions: live loads and regularly distributed through all bays. Frames are rigid, moment amplification factors less than 1.4. Members excluded from the approximate methods: non-rectangular frames, pitched portal frame, pitch more than 150, beams with relatively high axial compressive loads, highly irregularly distributed loads, or complex geometry. So for all these cases, we must perform a second order analysis or rational frame backlink analysis. So if the second or amplification factor is not working, so we need to perform second order analysis. Braised or rectangular frames also normally fall into the unity amplification category if their columns are bent in double curvature. Okay, so the braised rectangular frames are fall into the unity amplification factor. So the amplification factor delta B is equal to 1, so it is not working, or not, it is useless because there is no increasing or no amplification of the moment. Trusses and other triangulated frames of light to medium construction would normally need no second order analysis. Bending moment are normally quite small. So also in trusses and triangulated frames, there is no need for second order analysis because the moments are small. Second, for Australian standard AS 4100, second order effects are less than 10% may be neglected. So if the second order effects are less than 10%, they can be neglected. In general, factors increasing moment amplification factors are high ratios of design compressive axial forces, high ratios of design compressive axial forces to elastic flexure buckling load, so N star to NOMB. Bending moments producing single curvature, bending combining with relatively high axial load. So if you have like member under single curvature, so something with high axial load. So axial load high and single curvature. So this will cause high amplification factor. So high amplification factor comes with the two cases we have talked about. And this table is suggested method of analysis of the amplification factor. So this is what we have been talking about. So delta B equal to Cm over 1 minus N star over N OMB. Tension member, there is no, because tension, so delta B equal to 1. This has no axial force. So in this one, tension member, this is the general rule of braced. This tension, so equal delta B equal to 1. This no axial force, so delta B also equal to 1. This also UDL with N, so general case. This is also a general case because it has N and uniform load. But because it is sway, so we need to calculate delta B, delta S, and calculate delta M. This is a truss. So delta B is equal to 1 if it is light. and so on. So you have several example here. For example, this is here. Let's see here, number 8. We have sway member and braced member. So delta for braced, delta B. You have to calculate delta B for the braced member. You have to calculate delta S for sway member. Okay, where this is HS and this is delta S. So you can calculate delta S and delta B. Okay, and that's it for the first part. Thank you.